Hello everyone, welcome to Smart Interviews. So today we are going to solve a problem called Lowest Common Ancestor in a binary tree from LeetCode. You can find the problem link in the description below. I highly recommend you guys to pause the video over here, open the problem statement, understand it thoroughly, and try to come up with a solution on your own. Alright, let's get started. So if you look at this, the problem says that you are given a binary tree. You have to find the lowest common ancestor, that is the LCA, of the two given nodes. The LCA is defined between two nodes P and Q as the lowest node in the tree that has both P and Q as descendants, where we allow a node to be a descendant of itself as well. If you look at the first example, for this given tree, the two given nodes are 5 and 1. If you look at the nodes 5 and 1, they only have one common ancestor, which is 3. Hence, the answer is 3. If you look at the second example, for the two given nodes 5 and 4, you have two common ancestors, which are 3 and 5. The lowest out of them is 5. Hence, 5 is the answer. Let us try to understand the problem statement better. Say for instance, you are given this tree in the input, and say the given two nodes P and Q are 2 and 4. Basically, this node 2 and this node 4. If you look at it more closely, the nodes 2 and 4 have two common ancestors, which are 3 and 10. So one way to look at this is, if you traverse from the root node to the node 2, you will see that the nodes from root to 2 are 3, 10 and 2. If you look at the nodes from root node to the node 4, you will see that the nodes are 3, 10, 5, 25 and 4. If you can somehow store these nodes in two different lists, say list 1 and list 2, after you are done with that, you can simply iterate on the list and find the common ancestors. So if you observe these two lists, the common ancestors are 3 and 10, and out of them, as per the problem statement, we should be printing the lowest common ancestor. Lowest common ancestors in terms of comparing through the root of the tree. So out of 3 and 10, the lowest is 10. I hope you guys understand ancestors and descendants. So if you look at the node 18, all of these nodes are descendants of 18. And if you look at all of these nodes, 18 is ancestor for all of them. Even 3 is ancestor for all of them. So in short, the root node is ancestor for all the nodes of the given tree. So as we discussed, one way is we somehow store the nodes in the path from root node to the node P, and in the path from the root node to the node Q, and then we find the lowest common ancestor by simply iterating on the two list. That is one way of doing it. As a different solution, we can try to use the power of simply searching the tree for the two nodes P and Q. The idea behind this is, if you are at a node say n, and if you are finding one of the two nodes on the left side of n, and if you are finding the other node on the right side of n, it means this node n becomes the LCA. So we are going to search for both the nodes P and Q at the same time in the tree, and the moment we encounter a node where one of the nodes are found on the left side, one of the nodes are found on the right side, then this current node, this becomes the LCA. Let's try to trace out this logic on the current example. Say the given nodes are 2 and 4. So your P is 2 and your Q is 4. We'll start by searching through the root node. We'll go to the left side. We are not finding P or Q yet. Again, if we continue, we go to the left side. Here we observe that this node 2 is matching with P or Q. The moment we have found a match, there is no requirement for us to go to the below subtree. We can simply return back from here the same node that we found. Let's say this node is A. So we are returning A from here. Now if we continue our search on the right side, we go to 5. We go to the left of 5. We reached a null node. There is nothing over here. So from here, we'll simply return null, saying that we have not found anything in this subtree. Now we continue our search on the right side. We reach 25. We go to left. We reach here. Nothing is found. We'll return null from there. Again, we search on the right side. Nothing is found. We return null from there. Now for this node, both searches in the left and right return null. It means that we did not find either of the two nodes P or Q in this subtree. So this node should also be returning null. Now if you look at the node 25, from the left subtree, we got null. We'll continue our search on the right side. The moment you reach here, it is matching with one of the two nodes P or Q. So from here, we'll return this node itself. Let us say this node is B. So we are returning B itself from here. Now for this node 25, from the left side we got null, from the right side we got B. It means we have found one of the relevant nodes. So we should return the same node that we have found, that is B. Again, same scenario for this node 5. We have found null on the left side. We have found B on the right side. So we'll return B itself. Now this is where things gets interesting. If you look at the node 10, on the left side we found the node A, and on the right side we found the node B. So as discussed previously, the moment you encounter a node where you have found one of the nodes on the left side and another node on the right side, this current node becomes the LCA. That's what exactly where we are. So if you look at this, on the left side we have found A, and on the right side we have found B. So this becomes the LCA. So from here we'll return 10 itself. Let's say this node is X. So from here we are returning X. Now for this node, we got X from the left side. As of now, it doesn't know that we have found the LCA. So it will continue searching on the right side. When we search on the right side, in this entire subtree, we will not find either X or Y, that is either P or Q will not be found in this subtree. This entire subtree will be returning null. Now if you look at the current node, it got X from the left side and it got null from the right side. So as we discussed previously, this will return x, which is nothing but 10. So we will be finding our required answer. That's one scenario where P and Q, the two given nodes, are not ancestor of each other. If you look at a different scenario, say the given two nodes are 20 and 8. It is different from the previous scenario because here one of the two nodes out of 20 and 8 is itself the answer. If you see, 20 is the common ancestor now. If you trace out the same logic for this example, you will see that when we search on the left side from the root node, we will not find any of the two nodes on the left side. So this will be returning null. When we search on the right side, first we'll go to 18. From 18, we'll search on the left of 18. We will not find anything. We'll be returning null. Then we will go to the right of 18. The moment we reach this node, we realize that we have found one of the two nodes given in the input. So from here, we will not continue to the further subtree. We'll return the same node. Say this node is t. So we are returning t. Now for this node, we got null from the left subtree and we got t from the right subtree. So this node will return the value which it has found so far, which is t itself. Again for this node, left call gave it null, right call gave it t, so it will return t itself. So now that we understand both the scenarios, let us try to summarize it. For a node, if you find something on left and if you find something on right, then the current node becomes the LCA. That's the first scenario. Second scenario, for a node, if you find something on left but you do not find anything on right, you return whatever you have found on the left side because that may be the answer. That's the second scenario. Third scenario, similar to the second scenario, if you find something on the right side but you do not find anything on the left side, you simply return whatever you have found in the right call. And the fourth scenario, for a node, if there is nothing on left and there is nothing on right, you simply return null, stating that you have not found any relevant node so far. Now let's try to code up this logic. Again, I highly recommend everyone to pause the video here, understand the logic thoroughly, and try to convert the logic to code on your own. You can use any language of your choice. So let's try to code it up. We'll go with the code in C++. As we discussed, the first thing that we'll do is search both the nodes in left subtree and right subtree. So we are going to search it in the left subtree first. So we are going to call the function lowest common ancestor with root left and the two nodes P and Q. We'll do the exact same thing to search in the right subtree. We'll again call the same function, which is lowest common ancestor, and we will pass root right comma P comma Q. Now four scenarios as we talked about. If we found something on the left, that is left is not null, and we found something on the right, that is right is not null, we should return the current node as the LCA. This is the first scenario. Second scenario, if we found something on the left and we did not find something on the right, that is left is not null but right is null, we will return whatever we found on the left side. Similar scenario for the right side. If we did not find anything on left and we found something on the right, we will return whatever we found on the right side. Last scenario, both left and right are null, so we will simply return null from there. Shall we try to run the code and see whether it works or not? Let's try it out. One of the most common mistakes that people do while writing recursive code is that we forget the base condition. In recursive code, it's very important that you always write a base condition. So one base condition will be if root is null, as we already saw while tracing out on the given example. If root is null, we should return null from there, stating that we did not find anything relevant. Second thing, we also discussed that the moment we find either P or Q, we return back the same node, stating that we have found one of the two nodes. So if root is equal to P or root is equal to Q, we'll return that node. Now let's see, let's try to run the code again. So if you see, it's working for all the three sample inputs. Let's try to submit and check whether it works for the hidden test cases as well. So once we submit, we saw that the code is working for all hidden test cases. You can also simplify the code. For instance, this condition says that if you find something on left as well as right, current node is the LCA. But otherwise, we'll simply return whatever we found. So instead of writing these three separately, you can simply write if left is not equal to null, we'll return left, otherwise we'll return right. This will cover all the three scenarios in a single statement. Let's try to run and check. It's working for the sample test cases. Let's submit. It's also working for the hidden test cases. Now, if anyone is not familiar with C++, let's see how you can write the same code in Java. I'll just copy the code for reference and we'll switch our language to Java. Let us paste the C++ code over here. So if you're familiar with Java, in Java, we write null in this manner. So everywhere we are using null, we'll replace it. Here, here, as well as here. Also, to access the data within the nodes, we'll be using a dot operator. And since it's a Java class, it doesn't have pointer. So this will be gone as well. That's it. That should make it work in Java. So if you run the code, you see that it's working for the sample. Let's submit. And it got accepted. Great. Let us look at another similar problem. This problem says that you have to find the lowest common ancestor of a binary search tree. Instead of a binary tree, you are given a binary search tree. If you look at the first example, the given two nodes are 2 and 8. The nodes 2 and 8 have only a common ancestor, which is 6. Hence, 6 is the answer. If you look at the second example, for the nodes 2 and 4, there are two common ancestors, which are 6 and 2. But 2 is the lowest one, so that becomes the LCA. Now, what do you guys think? Can we reuse the same logic that we use for binary tree? Like if I go over here and if I paste the exact same code that we use for a binary tree, will that work? Of course, binary search tree has additional properties, but if we just skip those properties for now and just treat it as a binary tree, will it work? So I pasted the exact same code. Let's try to run and check. So when I run, it's running for the sample test cases successfully. And if we submit, it's getting accepted successfully. So we can reuse the exact same code for this problem. However, binary search tree, that is a BST, has additional properties. And let us see if we can use those properties to come up with a better solution. So say you were given this tree in the input. BST has a property that all the nodes in the left subtree will be less than the root node, and the root node will be less than all the nodes in the right subtree. And this property is applicable for every node. So if you observe here, all of these nodes are less than 25 and all of these nodes are greater than 25. Similarly, if you see over here, all the nodes on the left subtree of 8 are less than 8. All the nodes in the right subtree of 8 are greater than 8. So these are the BST properties. Now say the given two nodes were 12 and 24. So you can see that 12 is over here and 24 is over here. Now in the previous logic, we were searching the entire tree for the given two nodes P and Q. But in a BST, the moment you start searching from the root node, you realize that both 12 and 24 are less than 25. So instead of searching in the entire tree, we can only search in the left subtree. So we can skip this entire part and we can just continue with our search on the left side. Once we reach here, we'll realize that both the given nodes P and Q are greater than 8. So we will skip the entire left subtree and we'll continue our search only on the right side. When we reach here, we realize that one of the nodes is less than 15 and one of them is greater than 15. So it definitely means that this is the point where the search will split into left part and right part. So from that we can say that 15 is definitely the LCA which we are looking for. So very similar to the previous logic, if for a node you are going to find something on the left and you're going to find something on the right, that current node becomes the LCA. In this example, we do not have to actually search for it. The moment we reach 15 and we see that 12 is less than 15 and 24 is greater than 15, we can stop and return 15 from here itself. Let's try to continue our trace. Let's say this node is T and we are returning T. We should return whatever we got from the call. So we got T, we'll return the same T. Again from here, we got T, we'll return the same T. So if you observe carefully, we are not searching the entire tree, we are searching only a part of it, which will help us optimize the complexity. Let's take the second scenario as well. Say for example, you are given the two nodes as 58 and 48. You have 48 over here and you have 58 over here. Again, we'll use the property of a BST. We will start from the root node. We start from 25. you will see that both P and Q are greater than 25. So you'll continue to search only in the right side. You'll be skipping the entire left subtree. Again at 43, you'll realize that both P and Q are greater than 43. You'll continue searching only in the right side. The moment you reach this, that is, it is matching with one of the two nodes, P or Q, you'll return the same node. Let's say this node is S. We will return whatever we got from the function call. We got S, we are returning S. Again we got S, we are returning S. So if you see, the same logic covers this scenario as well, where one of the two given nodes is the answer, that is, one of them is the ancestor for both the nodes. So very similar to the previous problem, if you find something on both left and right, current node is the answer. However, in this implementation, we do not have to search on left and right. The moment we realize that one of them is less than the node and one of them is greater than the node, we return the current node as the LCA. That's it. That's the logic for this. If you compare with the previous logic, in the previous logic, we were iterating on all the nodes of the tree, which was giving us a time complexity of big O of n, because we were traversing the entire tree. But if you look at the current solution, in this solution, we are skipping either left or right in every function call. That is, we are going through every level of the binary tree exactly once. We are not going through each and every node. It reduces our complexity from big O of n to big O of h, where h is nothing but height of the tree. And as some of you may already know, height in worst case can be n if it's a skewed tree, and height in best case can be log n if it's a balanced binary search tree. So this solution is better than the previous solution. We are able to use the properties of a BST to come up with an efficient solution. Now let's try to code it up. Again, I recommend everyone to pause the video over here and try to convert the logic to code on your own. So if you try to convert the current logic into code, the base condition will remain same. If you get null, you'll return null. The moment you find either P or Q, you'll return that node. The remaining code will change. Let us clean it up. So we discussed that if the data in P is less than root and the data in Q is also less than root, it means we should simply search only on the left side. So we will continue our search, that is, we'll call the function lowest common ancestor with root left and the nodes P and Q. And we will return back whatever we get from the function call. The same thing we'll do for the right subtree. That is, if the data in P is greater than the data in root and the data in Q as well is greater than the data in root, in this scenario, we should search only on the right side and we will return whatever we get from the right function call. So we return lowest common ancestor of root right, comma, P, comma, Q. And at the end, we realize that one of them is definitely less, one of them is definitely more. So we will simply return the root from here. That's it. That's the code. Let's see if it works. So we are running the code. It worked for the sample. We can also submit and see if it's working for the hidden test cases. It's working as expected. Like we discussed previously, once you understand the logic properly, you can easily convert that logic to code in any language of your choice. Even for this code, you can simplify it by just removing these two conditions. Because first thing, if it's not falling here, it means that either it is equal or it is on left and right. In both of them, we should be returning root. So we can clean up this condition, it's not required. Additionally, if you look at the problem statement, it says that P and Q will definitely exist in the BST. So that means you'll definitely find them. So there is no point of comparing with null. So your code can be as simple as this. We can try to run it again. It's working as expected. We can submit as well. So it worked for the hidden test cases as well. Great. I hope you learned something new with this video. I hope you learned how to simplify the logic to code conversion and how you can easily convert the logic into code as per your language of choice. Hope you liked the video and learned that logic is the most important thing. Once you are clear with the logic, you can easily convert that logic to your language of choice, be it C, C++, Java, Python, or any other language. Thanks for watching. Please like, share, and subscribe for more such content.